Hello, welcome to session number 21 in the series Analog Circuit Design. I'm Anurag Nigam, and we have covered quite a few topics. Now what I want to cover is some of the applications of operational amplifiers, right? So let's start with the test book circuits. So I'm going to look at certain amplifiers, right? So I'm going to look at first inverting amplifier. Right now, this inverting amplifier is an OpAmp which has a feedback resistance over here. So let's consider this to be a negative or inverting terminal, and this is a non-inverting terminal, and I have a output voltage here VO, and I have an input resistance here R1, and then a feedback resistance RF. Okay, and then VI is applied over here, and I just want to keep the impedance to be same on both inverting and non-inverting, so I will have a R1 in parallel with RF over here. Okay, so for this amplifier, what's happening is that this is at 0, correct? So this is a small signal ground, and so this is supposed to be a small signal ground too, and what that means is the current which flows as input current IN would be given by IN would be equal to VI over R1. Now this current is the current doesn't flow into the inverting input because it's a capacitive in nature, so this whole current will flow this way, and this will cause a voltage over here, so the output VO would be equal to minus of this current IN into RF, which would be equal to minus RF upon R1 times of VI. So the gain AV would be equal to VO over VI is equal to minus RF over R1. Right. So now this is the gain of the inverting amplifier. Let's see what happens in case of a non-inverting amplifier. So I'll put here a non-inverting amplifier. Okay, in case of a non-inverting amplifier, only the inputs are swapped. So this is my OpAmp, and this has got inverting input and a non-inverting input here, and an output here VO. And here what I'll do is, instead of applying input to the inverting terminal, and this is still RF, this is still R1, and this is ground, and I will apply input over here. Now there is no DC current drawn, I can always put a equivalent here, which is R1 in parallel with RF, and I am going to apply to this. So in both cases you will have to give a DC VCM. So this is a DC value, while I'm talking about this is a small signal voltage. So this is a small signal 0 volts. So both terminals sitting at VCM. Okay, so here I can always apply input over here, right? I can always apply the input over here. Actually, the right way to do is that it should have a capacitive coupling of Vi over here, and VCM you are going to create over here. Similarly, here you are going to generate a VCM. So I can put here VCM, and right, and in this case here I'll put VCM, and I should do a capacitive coupling over here. This can be a large capacitor Vi. That's one way of doing it. I can do the other way is because nothing flows in here, this voltage will still be that, so I can always apply input right here. This will be Vi plus VCM. Okay, so that will be okay. And what will happen is so Vi is applied over here, and same small signal Vi is over here. So what we have here is VO divided by RF plus R1 multiplied by R1 should be equal to Vi, or VO divided by Vi should be equal to 1 plus RF upon R1 times of, yeah, so that will be the gain. So this is a non-inverting gain. So I am going to implement these two amplifiers in here. So let's go ahead and create a new schematic, call it as INV AMP, correct? In here I am going to put an OpAmp from the OpAmp circuits, 3-stage OpAmp, because there is a feedback resistor, so there is a resistive load. So I am going to just move the text to the right, and here I am going to put in what you call a current which I draw from this, which is 20 microamperes, and then there is a ground here. So why would it do that? Okay, so and then there is a ground here. That's strange. Okay, so there's a ground here. Now, is there an annotate DC on? Hang on. Simulate. Nothing is on. Why does it show 0 volt? Anyways, this is going to be 20 microamperes. Right, and if I want, I can move this to the side. Okay, so this is clear. Now I'm going to have a VDD which is going to be 2.4 volts. So I don't know why it is giving these strange voltages. 2.4 volts. Okay, and then I am going to have input. So I'll go to lump components. I have a RF which is like, let's say, keep 100k, and then R1 as 0.1k, so that's a gain of 100. So that is equal to 40 dB gain, sorry. So this is 100k, and this is going to be 0.1k, right? Done. And I'm going to connect these two resistors as is over here. 1, 2, right? Okay, so what I can do is I can put a common mode voltage through this. Now there is no voltage drop across here, so for reason it is giving complicated, it's giving stupid numbers here. Don't worry about it. Maybe the previous simulation crashed. Maybe because of that is doing something. Oh, not print. Okay, so I am going to put in here a common mode voltage of 1.2. Reason being that 1.2, there's a large input common mode voltage range, but 1.2 is somewhere halfway between, so I'm going to put this as 1.2. Right, so now we are all set for simulation. I'll put here a AC source, simulation frequency, sources frequency domain, VAC. I have to put VAC, not V1 tone. Right, and one thing more you have to notice is I have to put here a common mode voltage. So let's create a variable VCM, and this VCM is 1.2. VCM is 1.2, and that VCM is a common mode here. And similarly here the DC value would be VCM. Okay, so both are VCM, common mode voltage, right? Now I want to observe VO, which is over here, and we are all set. All we need is a include file, which is over here, and then I need to do a DC simulation on this. Sorry, AC simulation, simulation AC. Okay, and in this case I want to do a log sweep. So I'm going to go from 1 Hertz to 10 gigahertz log, and I want to put 80 points per decade. And in the display, start, stop, and decade is what I'm going to do. So this is my AC simulation. This is all set, and I'm going to hit simulate. One more thing. Okay, so let me just move this text up. Fine. Okay, so now I'm going to plot here VO, and this I'm going to put here in the log scale of x-axis. So this is almost a 40 dB gain, slightly lower than 40 dB. So this is what we designed for. Almost 40 dB gain. And next what I'm going to do is I'm going to display here from the open loop OpAmp, which is 3-stage OpAmp. I'm going to put here its gain, and this one I am going to make blue and dashed. So now you can see we had a 60 dB gain, and now it is minus RF upon R1, which is going to be a ratio of 100 or 40 dB. Next thing I want to do here is I want to look at the phase, and this phase I want to put on the right hand axis, and also I want to unwrap the rollover. So I will say unwrap this phase, so it will not just jump back to 0 after 360. Okay, so that's the phase. Let's make it green colored and thick. Okay, so if you see, phase is 180, so look in the right hand side. So if I put a marker, that's a phase of 180, right? So that's a phase of 180, and I'll put one marker over here just to look at what is the margin. So here, by the time it rolls over to, by the time it rolls over to 0, the gain is right now 2 degrees. 2 degrees. Okay, so it does become negative 1 milli. Okay, so now this is a unity gain bandwidth of 446 megahertz, and yeah, and the margin is 67 or 68 degrees. Okay, so that's the story for a inverting amplifier. Now I am going to just make a copy of this. So where did I create it? Inverting amplifier, where did it go? In gain stages, maybe. Yes, so I'll make a copy of it, copy cell, and I will call it a non-inverting amplifier, NI, and this goes under gain stages. Okay, so I have the non-inverting amplifier over here. So all I'm going to change is I'm going to swap this one. Okay, this one gets connected to over here, and this one gets connected over here. Okay, so now I'm going to simulate this one, and the gain would be slightly higher. I'll put a log scale on x-axis, so it is the same response, but I'm going to put in here a marker to see. So it's slightly higher, doesn't matter. And then I'll compare it to the open loop gain from here, and this one I'm going to do a dash. Okay, so this is the open loop gain, and let's plot the phase, and let's put the phase on the right hand side axis. Okay, and I have to put an unwrap on this because there is a rollover, so I'll put here unwrap, and that's it. I'll change the color of this to be green so that you can easily see it. Okay, notice again the margin is almost the same, right? No, because there is a rollover from 0, there will be a lot more margin, right? Okay, so I'll put here. Okay, so if you look at the phase, it's 180 degrees. Oh, sorry, it's 0. So in case of inverting amplifier, you have minus 180, and in case of non-inverting, it is 0. Or so that's what an inverting amplifier response is going to be. Now I want to look at some other circuits. Okay, so these are the gain stages. So let's go back to the drawing board here. Okay, so now what I'm going to do is, instead of RF, so let's have the same circuit here. Sorry. we'll have the same circuit over here. We have a negative non-inverting here, and I am going to put here R1, and I am going to put here C, and then this is VO, and this is VI, and then this I would keep as R1 C, not C1, C, and then I'll give it a VCM. Okay, and this one will have VCM. Fine. So what's going to happen is, this is a small signal 0. So this is small signal. So the current is VI over R1. So this is your IN. And then there is a capacitor which charges this A. So I assume that the initial charge on capacitor is 0. So I have 1 over C integral I dt. I is going to be VI over R1 times of dt, and this will be equal to VO. And so VO is going to be, and this will be a negative number, minus 1 over R1C times of integral VI times of dt. So this is an equation of a integrator. So I have an integrator over here. So what I have discussed here is an integrator. And then I'm going to talk about differentiator. Okay, and for a differentiator, what do I have? I have the same OpAmp. Sorry, I have the same OpAmp over here. Come on. And this is an inverting, this is a non-inverting, and I have a capacitor on the input. So this is VI, and then I have a resistor here as RF, and this is output VO, and this is going to be RF in parallel with C. And now I am going to put in again a VCM from here. Right, so this is a small signal ground, this is a small signal ground. So now the current which flows in the capacitor is CdV by dt, CdV by dt, and this current continues to flow this way. Okay, so this will be RF times of minus RF times of CdV by dt. That's going to be VO. So we have VO is equal to minus RF C times of dVi by dt. So this is a differential of the input voltage signal. So this is how a differentiator would work. So now okay, so now let's implement this differentiator and integrator in our circuit. So if I give a square wave input to a differentiator, it will become triangular. If I give a triangular wave input to a if I give a square wave to an integrator, it will become a triangular wave. And if I give a triangular wave to a differentiator, it will become a square wave. So let's try that. Or if I give a sine, it will become a cosine, and if I give a cosine, it will become a sine, right? So let me see if I'm recording. 24 minutes into recording. Okay, so let's look at an integrator. So what I'll do is I'll use a sine wave, which, a square wave which is generated by a IC555. So that's over here, and I will say copy cell, and I will say integrator 1. Okay, and I'm going to copy this in the same OpAmp based circuits folder, and say OK. So I have it over here. Okay, so the next thing I'm going to do is I'm going to put in an integrator over here. So Q is a square wave. I want to see what it looks like, right? So what I'll do is, let's say if I have an inverting amplifier, right? So I'll just copy it from there. Gain stages, inverting amplifier, schematic. So what I'm going to copy is everything. Yeah, almost everything I'll copy here. Okay, and here I don't want this, so I'll say edit, copy, and edit, paste, and I'm gonna flip this. So I'm gonna flip it in this direction. Okay, so now what do I have here? Okay, I'm going to put in F5. Okay, so here I'm going to put in a 40 kilo ohm resistor, right? And here the resistor is going to be 40. Okay, and here instead of this I'm going to put here a capacitor, which is the same size capacitor which is over here, this one. So I'll just copy here this one, rotate, place it here, then make a copy of this again, and I'm going to place it over here. Okay, so now this is set. I just need one supply, so I can draw from the same supply, and I can just connect this, so I can bring it close. Okay, so I am giving an input. Just one second. Okay, I'm giving it a input which is a square wave, and I am looking at VO as the output. This is biased this way, and VCM over here is going to be 1.2 volts, correct? And then the supply is going to be this one, right? Okay, so let's connect the supply. Okay, so Q is going to be a square wave, and VO should be a triangular wave, right? And I would do it for 150 microsecond, and then I would have 0.1 microsecond is the time. So let's simulate this. So I'm going to first plot Q to be sure that what it is. So that's a Q. I'm going to forget about the first 10 or 20 nanosecond. So I am going to go from 10 nanosecond to 150 nanoseconds, right? So I'm going to go from 10 nanoseconds to 10e minus 9 to 150 nanosecond, 150 e minus 9 in steps of, let's say, 10 e minus 9, right? What happened here? Oh, not nano, micro, sorry. So 10 microsecond to 150 microsecond, 150 microsecond, sorry, in steps of 10 microsecond, let's say 10 microsecond. Okay, so now that makes sense. Okay, so this is our output square wave. Later we can zoom in if we want more, and then let's look at what happened to VO. And VO is a, okay, so it's not good enough. Okay, so let me just put a kind of a, so it has to be delayed, right? So let's say corner 7.5, and this is 7.5. Okay, let's see this again. Okay, so basically I rise RC times constant. Okay, that corner frequency is kind of messed up. Okay, yeah, so what you do is you have 0.69 nanofarad and 40 kilo as RC, and I just adjusted VCM to be 1.12, and then this square wave is converted to a triangular wave. Let's have a look at it. Okay, so there it is. This blue one is your triangular wave, right? Now I want to convert this triangular wave back to square wave. So let's say if I was to put a differentiator following this, would that do that? Okay, so what I'm going to do now is I'm going to have a differentiator following this integrator. So what I'm going to do is I'm going to copy this circuit as is, right? Copy this circuit as is over here, and I'm going to swap this so that it looks like a differentiator, correct? So this will go into the input over here, and that would be the output, like this. And all I have to do is give a different name to the output node as VO1, right? And just hit simulate. So once I do that, still have this triangular wave, right? So now let's say if I have converted that triangular wave, which is VO1, so this is the triangular wave, and I'm plotting from 10 micro to 150 micro, right? 10 micro to 150 micro, 150 micro in steps of 10 micro, 10 micro, right? What did I do? X-axis 10, 10 micro in steps of 10. So this is going to 150 micro, right? So I have a 10 micro going to 150 micro seconds in steps of 10 microseconds. So what's the problem here? 10 microseconds. Okay, so that's my triangular wave. Let's make it blue color so that you can identify it easily. Okay, so now this one has been given as input to a differentiator, and VO1 is the output. So this is my output. Obviously it is not clean. It's not clean over here, but it is still a square wave, right? Still a square wave. Now if you wish to clean this, I'll just put an inverter in front of it. It will be a pure square wave, right? So if that's the story, I can follow it with an inverter or a buffer or a NOT gate, right? So that would clean it up, but it is working, right? So you have so it's messing up over here because of this transition not being smooth. That may be because, let's bump this up a little. Okay, so it's cleaner now. Okay, so now I have converted, though tops are not clean, but the transitions are clean, isn't it? So I have converted a triangular wave into a square wave. So this is how a differentiator would work, an integrator and a differentiator. Now what else do I want to do? Okay, there is one more thing which I want to mention here, is a difference amplifier, right? And that would lead to what is called an instrumentation amplifier, right? So let's look at, okay, for a difference amplifier, I am going to have the same OpAmp like this, minus and plus, and this is my output, and these are my inputs. So I would have a R1 and I would have a RF, and I'm going to have R2 and I'm going to have a R3. This is VO, right? And I have got V minus and V plus, and in this case the output voltage VO by V plus minus V minus is going to be equal to RF upon R1, provided a constraint. I choose R3 upon R2 same as RF upon R1. Okay, RF upon R1 is equal to R3 upon R2. Okay, so this would be a difference amplifier, right? Now there are other things which you can do with this, like a summing amplifier, right? And a summing amplifier would be an OpAmp right, and in this case you are going to have RF, and then you are going to have R1, R2, R3, and so on. Now we know that this is 0, so this is 0, so all these currents are going to sum up and go this way, and that is why the output would be, so this is V1, V2, V3, so then the individual currents would be V1 by R1 plus V2 by R2 plus V3 by R3 and so on, and then this is multiplied by RF, for example, so that will give you minus of VO. So that means that VO is equal to minus, so minus RF times of, each one is scaled by its own resistance. Okay, now this can be extended to something called R2R ladder network. Okay, R2R ladder network, and this, so this is a summing amplifier, that's a difference amplifier, right? So this is a difference amplifier, right? This one is a summing amplifier. And the next one is a DAC. So I'm going to use a R2R network. So here I'm going to start with a 2R, then I have a 2R here, and I have a V0 here, or rather A0. Okay, so let's have A0 over here, and then you have a R, and again a 2R, and then you have a A1 here, right? So this way, if you keep going, you can add as many bits as you like. Okay, so let me see if I'm recording it. Yeah, I'm recording it. So you can put, let's say, 4 bits for now. So we are going to try this one. This is 2R, sorry. This is 2R. This is going to be A2. Then this would be R again, and then there will be another 2R. And this will be A3. So these are 4 bits, and I'm going to give it to a OpAmp. So let's see. So I'm going to give this to a inverting input of a OpAmp. And here I'm going to terminate this into R by 2, and I'm going to put a VCM through here. So I'm going to put here a VCM, common mode voltage, and I am going to put here again R and VO. Okay, so what this is going to do is it is going to scale. So the net voltage, net impedance over here is for this whole network. Anywhere you look, you will find it is going to be R. So R and R here, so the gain is -1, right, in this case. And what is going to happen is A is going to be divided over this ladder, right? So basically A is going to be divided by 16, A1 is going to be divided by 8. Am I right? No. So this would be divided by 8, and this would be divided by, the current is basically dividing as you go away in the ladder. So this is dividing by 4, this is dividing by 2, and this is dividing by, sorry, this is dividing by 1. Okay, so what's happening is that this is going to be binary scaled. So now if I have a word, that would be converted to a analog output. So digital input would be converted to analog output, right? So that's what a DAC is. This is a R2R DAC. So we can try an R2R DAC, right? And to do that, we just go in here and look at the inverting amplifier and make a copy of this. Copy cell. Let me see if I'm recording it. Yeah, so I'll copy this cell to R2R DAC and say OK. And in here I am looking at R2R DAC, right? So it has gone under OpAmp circuits. Okay, so over here, so I'm going to take this and just modify this. Sorry. Okay, so all I have to do here is I'm just going to delete this and make some adjustments. Okay, so this is common mode, and let's put here a variable called RS. Okay, and RS value I'm putting somewhere around 1K. So let's put here RS. RS is around 1 kilo ohm. Apply. Okay, so RS is around 1 kilo ohm. So this is going to be RS kilo ohm, right? And this is going to be RS kilo ohm by 2. RS by 2. RS by 2 kilo ohm. Right. So this is RS by 2 kilo ohm. Hang on a second. Let's put a kilo ohm over here. Okay. And this one also. This is kilo ohm. Okay, so now I am going to create a ladder structure over here. Let's forget about this one, let's forget about this one, and let's just create the structure. Right, so I am going to have a 2R to start with. So I'm going to take this one and make it a 2R, twice of R. Right? Okay, so let's rotate this, and then you're going to start to have these. Right, so this is going to be A1, A0, and then you're going to have RS. And this pattern is going to repeat. Right, so this is going to repeat. A0, A1, A2, and then you have A3. So in case of A3, I'll just have one of this. So the net resistance is going to be RS, right? So net resistance is RS now. And okay, so I'm going to put in here 4 sources, and we know that the maximum frequency is around 250 kilohertz. So let's start with 200 kilohertz. So let's put here V pulse here, right? Sources frequency domain, and then there is a pulse over here. So this pulse, I am going to set this voltage to be, okay, common mode voltage is VCM. VCM, correct? And then the frequency I'm going to put here is 200 kilohertz, right? And accordingly, the width of the pulse would be 2.4549 microseconds or 2.5 microseconds, right? 2.49 microseconds. Okay, and then the rise time is 0.01 microseconds. Fall time is also, so it will be 0.01 microseconds. Fall time is 0.01 microseconds. Correct? So this is my first source. And the second one is going to be half the frequency because I want to generate all the states. Right? So I want to generate all the states. So the second one would be, I'll copy this to the right, and this one I'm going to put here as twice of this. So it will be 2.5. This will be a 4.99. 4.99. And this is going to be 100 kilohertz, right? And the next one, okay, the next one is going to be half of that. So let me just copy that. And over here I'll put 50 kilohertz, and this will be 9.99. Correct? And then the next one so the next one I'm going to put here is, just copy this, 25 kilohertz. Okay, so this will be 19.99. This is going to be 25 kilohertz. Okay, so I have my A0, A1, A2 and A3 set. So let's name them. So this one is A0, this one is A1, this one is going to be A2, this one is going to be A3. Let me see if it's recording. Yeah. Okay. So having done that, I am set with the simulations, right? Let's see. Everything looks okay to me. So these are all 2S's, 2RS, and this is all RS. So when I reach here, it will be RS, and this feeding into RS kilo ohms, and this is going to be RS by 2. That's fine. And then I'm going to have RS as 1 kilo ohm, which is set over here, and VCA is VCM equal to 1.5, for example. 5, right, and this is driven from 2.4 volts, and I guess I'm ready for simulations, right? I'm ready for simulations. Let me check, have a final check. VCM is 1.5, right? And I will simulate it for what duration? So this is going to be a time domain simulation. So I will go to simulation transient, and here I'm going to simulate for 80 microseconds in steps of 0.01 microsecond. So this will be 80 microseconds, and 0.01 microsecond step. Just 1 second. So this will be 0.01 microsecond. Correct? So now I have this for 80 microseconds. Let's check the time periods also. 2.5, 5, 10 and 20. Right, so that's fine. So I'm going to hit here simulate. So let's see. So what I'm doing with this binary scaling of time period is I'm running a counter here, right? So the counter will generate all the 16 states, and correspondingly the VO would be my output, right? Okay, so another application of this can be a Hartley or a Colpitts Oscillator, right? So another application. So we have seen a stable multivibrator using 555. Okay, so next I'm going to see is a oscillator, a Colpitts Oscillator. Okay, so what I'm going to plot here is, I want to plot here is first all the inputs, right? So first I'm going to plot all the inputs here. So I have A0. Let me see if it's going from 0 to 2 point. Okay, 1.5 to 2.5. Yeah, so it is going from 1.5 to 2.5, right? So here I'm going to put here A1, that's twice this thing. Then I'm going to put A2 and A3, and I'm going to split them out. So I'm going to split them out like this, and this one I'll make green so that it is clearly visible. Okay, so let's make it darker. So you see that I am going from, so I am running a counter here. Okay, so this is a counter which is running here, right? And I want to look at the output here. So I'm going to put here an output here, which is going to be VO. And that's what it is supposed to do, right? That's what it is supposed to do. It is going to be a DAC, right? And the concern is the linearity of the steps, but it is monotonic. That's the only achievement here. But what I'm trying to say here is, this is the simplest implementation of a DAC, R2R DAC, right? Okay, so next is one more application of this is going to be a Coil Pit Oscillator. So I'm going to put together a Coil Pit Oscillator, correct? So I'm going to go here, OpAmp circuits. I'm going to say new schematic, and I'll call this as, sorry, COLPITTSOSC, Coil Pit Oscillator. So I'm going to create the schematic, and then I'm going to use a 3-stage OpAmp. I can use a 2-stage also, because I'm not going to have any resistive parts here, right? So it's just a feedback, right? So let's use a 2-stage, because you know there is no concept of a current feedback here, right? So let's look for a 2-stage OpAmp. Okay, and then F5. Okay, and then I am going to put in here inductors and capacitors. You can compute the frequency and stuff like that, right? VCM. Okay, so I'm going to put a VCM here. So sources frequency domain, this is going to be 2.4 volts, and this I'm going to put here as 1.35 as a common mode input, right? That's around 2.7, so basically half the swing. That's what I'm doing here. So I'm somewhere in between the swing, right? And then I'm going to put here current source, which is going to be 20 is okay, 20 microamperes, correct? And if the oscillations don't happen, I'm going to reduce this current so as to increase the output resistances. But for now, let's just try this out, right? And then I'm going to put here a feedback. Okay, so I would have a feedback in here, CLC. Okay, CLC. So I'll go here to CLC. So I'll go to lump components. I'll pick up a L, and this L depends on 1/2 pi root of LC. That's how you are going to do that. So L I'm going to keep as 50 microhenry. 50 microhenry, and I'm going to give a certain loss to it. Let's say 1 ohm loss. Okay, wire wound inductors roughly would be like that. Okay, and then I'm going to put 2 capacitors which are going to be 0.5 nanohenry, 0.5 nanofarad. So 0.5 nanofarad, 0.5 nanofarad, right? So here is one, and then I'll just copy this guy over here. There's another one, and F5, move the text to the top, and this all three combination I'll move to the left so it is clear, and then I'll just put in a feedback. So this is a feedback path, right? Okay, so I'm ready with the Colpitts Oscillator. All I have to do is name the output node. So I'll name this node as VO, right? So that's a Colpitts Oscillator, and I'm going to do a transient simulation. So first of all, I have to put a include file. So from the library folder, put in the include file here. Okay, another thing is this is 2.4 volts, right? 2.4 volts. Okay, so I have put here that, and I'm going to do a transient simulation. Simulation transient. Here it is, and I'm going to simulate for 500 microseconds in steps of 0.01. 500 microseconds in steps of 0.01 microseconds. 0.01 microsecond. Okay, so now I am doing a transient simulation on this Colpitts Oscillator, and I am going to just hit simulate. And here I'm going to plot the output voltage, and it's oscillating, right? So let's zoom into a certain portion, and we will look at the frequency also. So let's just zoom into a certain portion and see the nature of oscillations. Okay, zoom further. Okay, this is oscillation, but this is not what the sine wave is, right? So what must be happening is you are hitting saturation somewhere. So let's do this, and let's hit this again. Okay, so it's not a sine wave, though it is oscillation. It is hitting this over here and clipping it out. So if it is clipping out, that means I change this one to be up a little, 38 maybe, and hit simulate again. So this is clipping here, right? Okay, just a second. Okay, so what I realized is, okay, I'm going to replace this 2-stage with a 3-stage, and there is a current limiting somewhere. So that's why I wanted to put an output stage as a source follower, and then hit the simulate again. And there your sine wave, right? So that's a Colpitts oscillator doing it for you, oscillations. If you want, you can also see its frequency response. So I will go in here, I will remove the scaling on the x-axis, auto scale, y-axis auto scale, and then here I want to put here fs. So if you go to expression and put here fs, you will know frequency of oscillation. Okay, and there you go, that's your frequency of oscillation. I'll put a marker on this. So it's oscillating at 1.4 megahertz. Okay, so this is a Colpitts oscillator using a OpAmp. Okay, So I'm gonna stop here. Thanks a lot.